Hello everyone. Now we will start the tensile testing of fabric. So, the strip test, which is very common for fabric tensile testing. So, here the samples are cut in 60 millimeter by 300 millimeter parallel to warp or weft. Okay. Suppose this is a fabric, as we have discussed in the sampling section. So, we cannot use the sample close to the selvage. So, we will select sample from here. The sample is cut. Suppose we want to test the warp strength. This is the sample we are cutting. The length is 30 centimeter and here it is a 6 centimeter. This is the length. Okay. Now, and after that what we do, this sample, it is a 30 centimeter and it is a 6 centimeter, and we start fraying out the yarn, because we have cut the yarn here fabric. So, it may so happen that the same warp, due to its some angle, same warp may not be continuing. What actually we want? We want the continuity in the warp, because we are trying to test the end. So, there during cutting it may so happen this one end it is cut in between, it goes in between its ending. So, in that, so we try to fray out the edge ends, edge yarns we are fraying out, to keep it, to bring it down to 5 centimeter. So, we are fraying out from both the sides to bring it the ultimately up to 5 centimeter, and also it is a 30 centimeter. So, 5 centimeter from top and 5 centimeter from bottom will go under the jaw. So, effectively it will become 20 centimeter length and 5 centimeter of width. This is the effective specimen size between the jaws. Okay. So, fraying the threads from both sides of the width to bring down width of effective width is it is 50 millimeter. Okay. So, 5 centimeter bringing down, and rate of extension is 50 millimeter per minute, and the gauge length is 20 centimeter. So, 5 as we have already mentioned. So, this is the effective specimen size and the rate is 50 millimeter per minute, and this is the instrument. So, then after that we just put in the jaw this fabric, and this constant rate of extension type of machine, here it is a bottom jaw is fixed and top jaw is moving and fabric gets extended, okay, stretched, and we measure the breaking load. If we see the animation here, now this started moving. Okay. Now, after clamping, it is clamped, gauge length is there, now it has not started moving. So, it is now it has started moving, and this bowing effect is there, that, and then it breaks. So, stress strain curve we can get from this. Okay. This is the stress strain curve, from there we can get the breaking load. This is the breaking load and this is the breaking extension. So, in this way we can calculate the energy required, everything we can calculate here. It is simply stress strain curve or load elongation curve of fabric. and the sample is pre-tensioned at 1% of probable breaking load. So, we know the, if we know the breaking load, it is probable breaking load, expected breaking load, we have to have some pre-tension. Why do we need pre-tension? Just to remove any crimp or any other fold, any crimp effect. So, we have some pre-tension, and in case of any improper jawing. So, suppose the jaw pressure is very high, in that case there may be some jaw breakage. So, that those fabrics we have to reject. Okay. Either there may be jaw breakage or maybe jaw slippage also. So, in that case, so the any breaks that occur within 5 millimeter of jaw should be rejected. That means, that within 5 millimeter means that had occurred within the jaw, after that it has come out, okay, due to extension. And for heavily milled, so fabric like where it is not possible to take out the threads, so we do not need to fray out. So, in that case we do not take the initial width of the sample 60 millimeter, we directly take 50 millimeter. So, directly our sample size, effective sample size we take, okay, and 30 millimeter, that is the size. Heavily milled fabric like woolen fabric, some felted fabric, this type of fabric we can use 50 millimeter by 300 millimeter gauge length. And similar to the tensile tester, another simple tester is the simple testing arrangement, which is called a grab test. And grab test basically it's in for most of the practical purpose, practical application, the strip test, strip tensile test, the result does not actually reflect the actual performance, because the any practical application we do not use as a strip as a sample, maybe in our apparel or maybe in any technical textile. Like in geotextile, if we see a fabric is placed under the soil, where the stones are there. Okay. It is not in the form of strip, it is the total fabric width and the gripping point is somewhere else at in between. So, that is even in the apparel, suppose it is being loaded, it is I want to have some stress value on the fabric. The fabric here it is not in the form of strip, here actually it is a grabbed in between. So, it is fundamentally it is different from the strip test. Jaw faces are considerably narrower than the actual fabric length. No need to fray the fabric, because we are actually gripping. Suppose this is the fabric and we are not gripping like strip test throughout the this width, we are gripping at the midpoint. Okay. So, we do not need to fray out the threads, actual sample is okay, and it is a quicker, we do not have to fray, we do not have to jaw it properly, you simply put cut the fabric and put under the this jaw, okay. And it is quicker method, and speed is adjusted so that the sample breaks at 20 plus minus 3 second, it is the same as the strip test also. Now, this is the grab test, this is total width, full width of the fabric, and here it is being grabbed, its jaws are much smaller in dimension, okay, width wise. So, basic issue here is that it gets assistance from the adjacent yarn, okay, adjacent yarns beyond the reach of this jaw. Okay. That means, it gets help. So, it adds to the strength of the fabric. So, effectively the grab strength is higher than the strip strength, because in strip strength only the yarns under this jaw, under the grip of the jaw are coming into picture, but here in addition to this adjacent fabric is also helping, but this grab strength result is actually it is very close to the practical value. Now, we will try to solve different numericals, okay, related to the strength of maybe bundle strength. We will try to solve numerical of fabric strength. First, let us see the Presley strength. Okay. It is a bundle strength. In a Presley fiber strength tester, the breaking load of cotton fiber bundle is 2.5 pound and mass is. So, in Presley strength tester or in stelometer, what we have to as I have mentioned, the jaw size of jaw or dimension of jaw are exactly same, they are interchangeable. Okay. And after breaking, so if we want to get the gram per text value, we must know the mass of the bundle. So, in this test always after testing we take the mass of the bundle. Okay. So, the cotton bundle is the breaking load is 2.5 pound and the mass of the bundle is 22 milligram. What is the Presley index and bundle tenacity in gram per text? So, this is the question. Now, it is a simple direct formula. Presley index is breaking load in pound and bundle weight in milligram, and if we want to convert the Presley index, as we have seen earlier, for 0 gauge length its a value is 5.3. Here it is given, it is a this is the 0 gauge length, you have found to be this, it is a in 0 gauge length form. Okay. So, this is the Presley index. So, 2.5 by 2, 1.25 is the Presley index and the length of the fiber bundle here in Presley for 0 gauge length, it is approximately 11.78 millimeter, approximately you can say 12 millimeter gauge length, and bundle tenacity in gram per text, if we multiply it by 5.36 for 0 gauge length, it is a 6.7 gram per text of the cotton. So, bundle strength, and this value it is in for 0 gauge length. Okay. So, why what is the 0 gauge length here? So, we must know the concept of 0 gauge length here. So, in if we see the Presley tester, this is the jaw, one jaw, another jaw is this one is another jaw. Okay. And if we have, if you see the fiber bundle, this is in almost parallel fiber bundle, and after that what we do, we cut this fabric, we cut this fabric by knife. Okay. Now, this is situation 1, and after the cutting okay, and this is the fibers. These are the fibers. Okay. Now, this length, Why 0 gauge length? There is no space between the fabric fiber, this is jaw. So, there is the gauge length, there is they are in contact, okay, these two jaws. This length is typically around say 11.8 millimeter, okay, 11.78 millimeter, or approximately say it is 12 millimeter. It is for 12 millimeter in stellometer. Okay. Now, this is the gauge length, and after that, after breakage, what happens? This will get disentangled and the fibers will be under the grip of the top jaw and bottom jaw. Then we have to open these fibers, and then this is from top jaw bundle, this is from say bottom jaw, and this total we have to take the mass, and as per this numerical it is a 2 milligram. And during and when in the machine, in the instrument, this will be loaded and the load will be measured here, okay, separating load. So, that is the situation here. So, this is the bundle strength here, it is coming out to be so 6.7, it is a directly we can use this formula. Okay. Next numerical is that stellometer. In stellometer, in addition to the 0 gauge length, there is a provision we can increase the gauge length to 3 millimeter. We can add one strip, metal strip, which is having 3 millimeter length, width, 3 millimeter thickness, that we can insert. So, that means the gauge length will be 3 millimeter, but effective length of the fiber bundle will be 12 millimeter plus 3 millimeter, it will become 15 millimeter. Okay. So, that is the thing, that situation. So, next problem is on stellometer. In a stellometer, the breaking load of cotton, of a cotton fiber bundle was found to be 1.5 kg and 0.994 kg with 0 and 3 millimeter gauge lengths respectively. Okay. And the mass of tested fiber bundles were 2 millimeter and 2.1 millimeter respectively. Okay. So, fiber bundles milligram, 2 milligram and 2.1 milligram respectively. What will be the bundle strength at 0 gauge length and at 3 millimeter gauge length? That is the question. Now, try to see the solution stepwise. The bundle tenacity is the breaking load in kg multiplied by length of the sample in millimeter divided by the mass of the fiber in milligram. So, fiber bundle, this is the standard formula to get the tenacity in terms of gram per tex. Okay. Same formula we can use for yarn also, gram per tex, only that the length of the yarn and the mass is required. Okay. So, this is the gram per tex. Now, the values are given. Okay. Which value is given? So, let us see the condition. Length of the fiber bundle in stellometer is approximately 12 millimeter with 0 gauge length and with 15 millimeter with 3 millimeter gauge length. Sample fiber jaw, okay, same fiber jaw is used as a Presley tester. With 3 millimeter gauge length, the length of the fiber bundle will become 15 millimeter. This data we know, that means the length of the sample is known here, okay, and mass is known and breaking load is known, then we can simply calculate. Okay. So, at 0 gauge length, the breaking load is given 1.25 kg, mass of sample is 2 milligram, and the bundle tenacity is come out to be 1.25 multiplied by 12, 12 is the length divided by the mass in milligram. So, it is coming out to be 7.5 gram per tex. Okay. Now, if we increase the same cotton, if we increase the this gauge length. So, we will get the value which will be lower than the 0 gauge length, because same factors like weak link effect, similar weak link effect will be there in bundle strength. If in other gauge length has increased, typically we should get the value lower than that. And one important thing is here, one has to mention here, we cannot always have bundle, even if the gauge length is constant like 0 gauge length, we cannot have the same bundle mass. Okay. Suppose for same 0 gauge length, we test the second sample, it may not be 2 milligram, it will be different, it may be little bit higher or lower, but accordingly it is expected that the breaking load will change. Okay. If it mass is more, that means breaking load will be proportionally higher, but ultimately the breaking bundle strength should be close to that. Okay. This is the value, and 3 millimeter gauge length, the breaking load is given, mass of sample is given, and bundle tenacity is here, it was 12 millimeter, and here in 3 millimeter gauge length it is becoming 15, and it is coming out to be 7.1 gram per tex cotton. Okay. So, that means what we are getting? We are getting little bit lower gram per tex for same cotton with higher gauge length. Okay. Next is that in a tensile tester, it is a yarn tenacity. In a tensile tester, the mean breaking load is of 30 tex yarn is 500 gram force. What is the tenacity of the yarn? It is very simple, simply divide it. Okay. It is a breaking load in gram force by linear density in tex. Okay. So, we can simply divide the gram force by tex, and it will give us the value 500 divided by 30, it is 16.67 gram per tex. Okay. This is the result. Now, next numerical is that it is a fabric tenacity. Okay. Now, normally in strip test we get the value in terms of kg or Newton or something. Okay. It is in terms of load value we get, but here it is asked that a tenacity, what will be the tenacity of fabric in gram per tex. If we see the fabric tenacity, it is normally not expressed in terms of load, it is expressed in terms of gram per tex, because if the width of the fabric changes, or if the say mass per unit area, just to compare the fabric of different mass per unit area, the tenacity value it is expressed in terms of gram per tex. Suppose for same fabric, similar, if I use instead of 200 gram per square meter, if I use say 300 gram per square meter, the breaking load value will definitely increase, but we have to see whether the tenacity value is increased or not. In that case, to compare the tenacity of fabric, actual the strength of the fabric, we have to compare in terms of gram per tex, not in terms of the breaking load. Breaking load will definitely be higher for thicker fabric. Okay. So, a fabric of aerial density 200 gram per square meter is tested in a tensile tester, that is strip tester, with 5 centimeter wide strip and 20 centimeter gauge length. Okay. So, what the data has been taken, it is a simple calculation we can take. Okay. The breaking load is found to be 45.5 kgf. Okay. What will be the tenacity of fabric in gram per tex? Okay. Now, this is the condition here. Now, the actual area of the fabric is 100 square centimeter, that means 0.01 square meter, and the mass of the test specimen is 2 gram, because 200 gram per square meter and 200 multiplied by 0.1, it is a 2 gram. Length of the strip is 0.2 meter, 20 centimeter, and we want to measure here the Tex value, Tex of the fabric under the test, and we know the Tex value, it is the mass of the sample by the length of the sample and mass of the specimen, length of the specimen multiplied by L is the in that particular unit, Tex unit, the L is the it is a 1000. So, we can use this value here. So, mass of the specimen 2 gram, length of the L is the 1000 meter, and the length of the specimen is 0.2 meter. So, it is coming out to be 10,000 Tex. Okay. And then what we can do, when the tenacity of the fabric we can calculate here, it is a breaking load in gram force per linear density in Tex, it is coming out to be 4.55 gram per Tex. Now, the idea of using gram per Tex in place of the breaking load, it is that suppose what we are doing, we are taking a fabric of say 300 gram per Tex, and what we have found that the strength has become say 50, say 50 strength, 50 gram per 50 kg force. Now, can we tell this fabric is stronger than earlier fabric? Earlier fabric it was 45.5. So, we cannot compare, because our this fabric is gram per square meter, this is areal density of the fabric is 300 gram per square meter, earlier it was 200 gram per square meter. So, this 300 gram per square meter fabric. So, if we try to see if we get the mass of the fabric, the keeping all other constant, the mass of the fabric will be 300 multiplied by 0.01, it is becoming 3 gram, and the Tex will be, what will be the Tex? 3 multiplied by 1000 by 0.2, that means it will become 15,000 Tex. Okay. 15,000 Tex, and the it is a 50 kg. So, 50 kg means 50,000 gram divided by 15,000, it will become say 10 by 3, okay, 10 by 3, okay, it is 10 by 3. So, it will be 3.33 gram per Tex. Okay. That means, earlier with the lower, even with the lower value of breaking load, the tenacity was 4.55, it is higher than this tenacity 3.33. That means, the breaking load with, we cannot compare the breaking load by breaking load of different types of fabric. Okay. So, to compare the breaking tenacity to the strength of the fabric, we should compare in terms of tenacity of the fabric, in terms of gram per Tex. So, here the idea is, first you have to get the value of Tex of the strip, okay, and then we can calculate. Okay. So, next the last segment we have reached here, it is basically, it gives us the another set of instrument, one instrument which is which works in CRE principle. The principle is same as that of single yarn strength testing, but this is fully automatic. In UTM we test the single yarn strength testing, we put in the jaw manually, but here Tensorapid, Worcester Tensorapid gives the automatic, the gripping and automatic braking. So, it is a for tensile testing of single yarn and ply yarn. So, we have to feed the yarn in the form of package, okay, for measurement of up to 1000 Newton, 1 kilonewton without exchanging the force transducer. Okay. So, it measure it is a wide range of tensile testing, one range of yarn we can test here. The clamping force, the yarn tensioner and the suction off of the yarn can be programmed. Okay. We can actually program depending on the yarn, type of yarn, we can program the clamping force, we can program the yarn tensioner, how much tension it has to put, and also the suction off of the yarn, okay, that how quickly the test will be done, and that we can program here. All numerical and graphical results are displayed on a video screen. Okay. On a video screen we can display everything, okay, in the form of histogram, load elongation curve and table form we can get. So, it is totally automatic, we have to only feed the cones or bobbins, mainly typically bobbin, ring bobbin you just put there, and it will automatically test data, large number of sample and give the histogram and everything it will give. In packages are up to 20 packages are actually put, we can in the creel we can put, and then it's automatically it measures the value, and as it is a program, it is all the data are kept in the memory, we can recall, we can for analysis, for future reference we can recall this. So, calling off of test parameters of frequently tested yarn type from the memory, we can just, there is memory, it is old version, there are 40, but now it has improved a lot. Pneumatically actuated yarn clamps. So, it is there is no physical pressure, it is a pneumatic pressure is there, and no spring, nothing is there, okay. And we can control the pressure, the clamping pressure is programmed. So, depending on the type of yarn we can program this clamping pressure, and electronic elongation measurement, it is elongation we can measure electronically, and test speed it is continuously you can adjust, automatically it can changed, it can be adjusted from 50 millimeter per minute to 5000 millimeter per minute. So, within that wide range we can change the test speed, test length can be changed, and this instrument work in two modes, in vertical mode and in also in horizontal mode. If it works in horizontal mode, it is continuously adjusted between 20 centimeter to 1 meter, okay. Within that range 20 centimeter to 1 meter range, that we can adjust the length, okay. It is a wide range, but in vertical mode it is a more range is higher, it is a say 10 centimeter to 1 meter. So, that within that range continuously we can adjust, okay. These are the simple parameters of the particular machine, but the working principle is exactly same that we have discussed. It is basically it works in the principle of strain gauge principle. we have reached at the end of the tensile tester. Here we have discussed all the tensile related parameters. We have discussed the different methods for measurement of tensile characteristics of textile material in the form of fiber bundle, in the form of single yarn, in the fabric, and also instrument for the dynamic measurement, that constantly winding tester. And we have also seen that the instruments work in different principles, that is constant rate of traverse, constant rate of elongation and constant rate of loading. And also we have seen there are various factors which affect the test result, like rate of elongation, the gauge length. So, if we want to have perfect result, so we have to follow the standard procedure, and also the test result can vary by improper jaw, improper placing of sample in the jaw. So, we must be very careful putting the fabric in the jaw. So, this I think with this that we will get overall idea about the tensile characteristics of textile material. We have also discussed various numericals which will enhance the better understanding of the principle, and hope this section will help in better understanding of the tensile characteristics, and also in application one can this this segment will help. Now, till then we will stop here, and will next class we will start with new topic. Till then, thank you.